The sound barrier was shattered back in 1947. For generations, that was the pinnacle of speed. But today, the internet is buzzing with a claim that sounds like it was ripped straight out of a sci-fi script. The story goes that the legendary engineering firm, Rolls-Royce, hasn't just left the sound barrier in the dust. They're supposedly breaking the laws of physics as we know them. Viral headlines and hushed whispers in engineering forums all tell the same tale. Rolls-Royce has built an engine that defies one of the most fundamental challenges of flight, an engine that can hit Mach 7, 7 times the speed of sound, without melting into a puddle of slag. They're calling it the ice-cool engine. But those viral headlines? They're missing the real story. This isn't just about a shiny new piece of tech. It's about a high-stakes geopolitical chess match that could shift the balance of global power forever. It's a story of incredible science, quiet rivalries, and a breakthrough that could rewrite the 21st century. So, we decided to investigate, to separate the hard engineering from the science fiction. And what we found is that the truth, well, it's even more interesting than the hype. To get your head around just how big a deal a Mach 7 air-breathing engine would be, you first have to understand the roadblock that stumped engineers for over 50 years. It isn't a wall of sound, it's a wall of fire. When a plane flies, it compresses the air in front of it. At a few hundred miles per hour, you barely notice. At Mach 1, that compression creates the famous sonic boom. But when you push past Mach 5, the official start of hypersonic flight, the physics gets extreme. At these speeds, the friction and compression are so intense that the air molecules themselves start to tear apart. This can create a sheath of superheated gas around the aircraft, with temperatures climbing past 2,000 degrees Celsius or 3,600 degrees Fahrenheit. For context, that's hotter than molten lava. It's certainly hot enough to threaten the high-strength titanium alloys used in the fastest jets ever built, if they were directly exposed to that kind of heat. This isn't just a theory. It's the single greatest barrier to hypersonic flight, a problem that has humbled the world's best engineers. Just look at the legendary SR-71 Blackbird. To this day, it's the fastest air-breathing, jet-powered aircraft in history, with a top speed over Mach 3.3. But flying that fast came at a wild cost. The Blackbird's titanium skin would heat up to over 300 degrees Celsius, causing the entire plane to stretch by several inches. It was famously designed to leak special jet fuel on the runway because its seals would only fit tightly once the plane got hot and expanded in the air. The SR-71 was a masterpiece, but it was flying at the absolute limit of what its materials could handle. Now, imagine trying to go more than twice as fast. At Mach 7, a conventional turbojet engine is a non-starter. For an engine like that to work, the air coming into its intake would be well over 1,000 degrees Celsius. No compressor blades on Earth, no matter what they're made of, can spin in that kind of heat. They'd glow cherry red, soften, and then shred themselves in an instant. This thermal nightmare is why hypersonic research has split into two main camps. First, you have scramjets. A scramjet, or supersonic combustion ramjet, is basically a cleverly shaped tube with no moving parts. It uses the aircraft's insane speed to compress air for combustion. Scramjets are incredibly powerful, but they have one huge catch. They only work at hypersonic speeds. They can't produce any thrust at a standstill, so they need a rocket to boost them up to Mach 4 or 5 before they can even light up. That makes them great for single-use missiles, but a headache for anything you want to reuse. Then you have rockets. Rockets carry their own oxygen, so they don't care how hot the outside air is. But lugging your own oxidizer around is incredibly inefficient. It adds enormous weight, which kills your range and payload. For decades, the holy grail has been a single, reusable engine that can do it all: breathe air, take off from a runway, blast through the sound barrier, punch through that wall of fire, and then come home to land. An engine that combines a jet's efficiency with a rocket's raw power. For the longest time, building an engine like that was pure fantasy. The materials didn't exist. The physics seemed impossible. Any attempt would just melt. So how did Rolls-Royce, according to the internet, solve a problem that's had engineers tearing their hair out for decades? They didn't fight the heat. They found a way to trick it. The piece of tech at the heart of this whole story is a device so revolutionary it feels like it's from the future. It's called a pre-cooler, and it's arguably one of the most important aerospace breakthroughs of this century. The idea sounds simple enough. If the air going into your engine is too hot, just cool it down. But the engineering to actually do that is mind-boggling. We're not talking about a car radiator here. At Mach 5, the air blasting into the engine is over 1,000 degrees Celsius. To make that air safe for a jet engine's turbine, you have to cool it down to around room temperature in less than 1/20th of a second. Pulling that off means managing a heat exchange of hundreds of megawatts. We're talking the output of a small power plant inside a device that has to be light enough to fly. It's been compared to dunking a white-hot piece of steel into liquid nitrogen and having it come out frosted in the blink of an eye. The secret to this impossible device is an intricate web of incredibly thin tubes. The pre-cooler is a heat exchanger made of kilometers of tubing with walls thinner than a human hair, all woven into a dense, complex matrix. A cryogenic fluid, liquid hydrogen in the engine's design, or helium in some test setups, pumps through these tubes at hundreds of degrees below zero. When the 1,000-degree air hits this network of frigid tubes, the heat is ripped out almost instantly. The inferno of hypersonic airflow is quenched, exiting the pre-cooler as a cold, dense, oxygen-rich gas, ready to be fed into a jet compressor. The engine basically inhales fire and exhales a blizzard. Now, while Rolls-Royce is the name in the viral headlines, the pioneering work on this tech was actually done by a brilliant British company called Reaction Engines. Their ambitious project is called SABRE, for Synergetic Air-Breathing Rocket Engine. Reaction Engines was backed early on by the UK government and BAE Systems, and Rolls-Royce is now a key strategic partner collaborating on the technology. The Sabre is designed as a true hybrid. It acts like a jet at lower speeds before switching to rocket mode to push a vehicle into orbit. And here's the key part. This isn't just a theory. In a series of groundbreaking tests at a special facility in Colorado, with partners like the US's DARPA, Reaction Engines proved it could work. They built a test rig that blasted the pre-cooler with a jet of air heated to over 1,000 degrees Celsius, simulating Mach 5 flight conditions. The pre-cooler didn't just survive, it worked perfectly, cooling the air in that fraction of a second. These tests proved the core idea wasn't a dream, but handling the heat is only half the problem. The other half is surviving it. The engine's core needs to be built from materials that can handle not just extreme temperatures, but also the shock of going from cold to hot and back again. This is where another quiet revolution is happening, in materials called ceramic matrix composites, or CMCs. Traditional engine parts are made of metal superalloys. They're strong, but they have a melting point. CMCs are different. They're made of ceramic fibers, like silicon carbide, woven into a ceramic matrix. This creates a material that's incredibly heat-resistant but also lightweight and tough. Unlike a ceramic plate that shatters, the fibers in a CMC can stop cracks from spreading. These materials can run at temperatures hundreds of degrees hotter than the best nickel alloys, and they weigh about a third as much. In aerospace, weight is everything. Lighter engines mean better fuel efficiency, more range, and higher performance. Companies like GE Aerospace are already using CMC parts in the turbine sections of modern engines, like the CFM LEAP. When you combine a super-efficient pre-cooler with a lightweight, heat-resistant CMC engine core, you suddenly have the recipe for a true, reusable hypersonic air-breathing engine. It's the key that unlocks the dream. An engine this powerful was never going to be just a science experiment. And this is where the story shifts from engineering to global power. If there's a number that keeps defense planners in Washington, Moscow, and Beijing up at night, it's not a dollar amount. It's Mach 5. The race to develop hypersonic weapons has been called a top national security priority by every major world power, kicking off what many see as a new arms race. For years, the United States, Russia, and China have poured billions into